Sounds good. Well, hi everyone. My name's Abigail, and I'm excited to be speaking to you all today as part of the WPI Value Creation Jam. And I'm really looking forward to sharing my team's proposal for a novel surgical approach for treating connective tissue tears. Ehlers-Danlos syndrome and other connective tissue disorders affect millions of people worldwide, causing debilitating pain, weakness, and disability. Injuries such as connective tissue tears are highly prevalent in these disorders, with currently no effective treatment options available. As current surgical approaches currently cause more harm than good, patients with connective tissue disorders are forced to live with these seemingly irreparable injuries. Our team's proposed solution is a next-generation biomimetic mesh scaffold seeded with cells designed to produce healthy collagen, thus encouraging wound healing through healthy tissue regeneration. To develop and test this solution, we have access to WPI's Regenerative Biomaterials Lab and Practice Point Medical Testing Facility. Our team has conducted thorough literature reviews and compiled lists of surgeon experts to interview and gauge feedback on our proposed idea. What sets our proposal apart is that it is a personalized approach that considers the patient's inherent disease state as opposed to assuming healthy tissue. Our biomedical solution will repair tears without the need for sutures, which are currently really harmful for sensitive tissues such as that in Ehlers-Danlos syndrome. Upon initial evaluation, our team believes that our solution outperforms existing surgical treatment, pain medication, and physical therapy in terms of efficacy, safety, cost, and recovery time. The ultimate value of our proposal is that it provides for end users is improved quality of life, reduced pain and complications, and potentially faster recovery times. Additionally, for funders or enterprises, our solution can yield improved patient outcomes and potential cost savings from a year-long therapies that don't address the root problem. Our biomimetic scaffold has the potential to significantly improve quality of life for millions of individuals suffering from connective tissue disorders. I thank you all for your time, and I look forward to working with you all.
Hi, everyone. Again, my name is Abigail Holmes, and I'm excited to share with you my idea for an arthroscopically deployed wound dressing to treat connective tissue tears. Now, when I was 12 years old, I tore through the labrum in my hip from simply standing up. It took years of hospitalizations, doctor's appointments, and pain medications to ultimately realize that I have Ehlers-Danlos syndrome, a chronic connective tissue disorder. I'm not alone in this, as 1 in 5,000 children each year are born with Ehlers-Danlos syndrome or EDS. EDS is present at birth and becomes continuously more debilitating with age. In fact, 88% of EDS patients report chronic joint pain and 61% report walking impairment. EDS is caused by a mutation in the gene that produces collagen in the body, which is detrimental considering that collagen is an essential structural support present in over 80% of the body. As seen here, healthy collagen is organized and linear in fashion, as opposed to the mutated collagen, which is nonlinear and disorganized, resulting in joint instability and weakened connective tissue. The current ecosystem is dire. EDS patients are prone to severe tissue tears after minimal physical trauma. This makes everyday activities such as standing up or even brushing your teeth potentially catastrophic. Tearing connective tissue in a joint can lead to significant pain, the possibility of permanent disability, and often requires corrective surgery. The problem is that current methods of surgical repair are ineffective on EDS patients due to weakened tissue. Alternative treatments such as physical therapy are standard protocols, even though they do not heal the injury or target the root cause of the pain and instability. The limiting factor is that traditional surgical suture methods do not account for weakened tissues and cause additional damage. Therefore, the need then exists to create an internal wound dressing that is arthroscopically deployable, adequately distributes mechanical strength, mimics the natural healing process, and maintains integrity for at least 5 years. I see a white space to provide a treatment for a chronic injury common among the 1.6 million EDS patients worldwide. I expect beachhead customers to be patients with a debilitating tear of 4 to 6 millimeters in the hip that would traditionally require surgery. The proposed approach is an arthroscopically deployed wound dressing to treat connective tissue tears. The solution consists of 2 main components: a therapeutic hydrogel infused with growth factors, which will be injected into the injured area, and a robust network of collagen fibers that will be 3D printed within the body. These collagen fibers will be integrated into the hydrogel to reinforce the wound dressing, evenly distribute load across the tissue, and guide the growth of healthy tissue. Now, let's take a step-by-step look at this approach. We begin with the injured labrum surrounded by inflammation and encompassed by healthy cells. Next, we're going to inject the hydrogel to fill the void created by the wound as well as to overlap with the healthy tissue area. Next, we'll arthroscopically bioprint the collagen fibers across the hydrogel and the wound site. This collagen scaffold will provide a mechanical and directional support for the cells to grow across. I expect that healthy tissue will proliferate from the scaffold and ultimately close the wound. I have identified the top 3 risks for this product as market adoption, efficacy, and scalability. I plan to mitigate these by discussing the approach with at least 10 orthopedic surgeons to assess feasibility, conducting thorough material testing to assess efficacy, and discussing the approach with manufacturers to design a product that is scalable beyond the lab bench. For end users, I anticipate that the approach will have surgical costs similar to current methods, which typically range from $7,000 to $32,000 depending on the severity of the injury. This cost is relatively small in comparison to the improved quality of life that it offers, allowing individuals to avoid the 28% increase in income required by those with physical disabilities and reducing chronic pain. As part of WPI's senior capstone project, I have received an initial investment of a little over $1,200 from WPI, which will be used to create a 3D cell culture model of EDS to be used for future testing of the treatment. As the product develops, R&D expenses will increase. However, this investment ultimately offers the advantage of gaining a share in the global wound closure market, which is valued at $13.7 billion. The main competitors for this method are traditional surgery, physical therapy, and pain medications. When it comes to EDS patients, traditional surgery presents several challenges. Sutures take twice as long, often lead to additional tears, and have a significantly higher risk of infection, which is why they are generally avoided. While physical therapy and pain medications can offer some relief to patients, they do not directly address the underlying injury. Based on a thorough literature review, there is currently no other research that's focusing on correcting tissue tears in EDS patients, indicating a lack of new competition in this field for at least a decade. The next phase of this project is taking place as a WPI MQP, in which I'm developing a cellular model of the impaired wound healing to be used for future testing. Now that a full literature review is complete, I'm moving into the design phase to be completed by December, followed by experimentation completed by March 2024, with the final publication being released before May 2024. The next steps would be to source seed funding and begin designing the treatment components. Thank you for your time, and I look forward to hearing your feedback.